Okay, so yeah, let's continue. I know there's no use crying for spilled water. Okay, so you guys didn't learn ADL 23234 tree B tree. Okay, from your data structure class. Okay, let me put it this way. Okay. Especially for ABL tree. I mean, at least you guys know the binary search tree, right? Binary search tree. I mean, your data structure teacher should have told you that. Last semester, right? 就是你们资料结构至少教过这个 binary search tree，就是二元搜寻术，对不对 ？So the problem, okay, the binary search tree is very nice. Like it allows you to insert, delete, okay, with a very nice property. But the issue is the tree may not be balanced, right? If the tree is always balanced, then the search, the insert, the delete can be done in log n amount of time. OK， 如果数是平衡的，那所有的那个 operation 都是可以很快速可以做到。But the issue is tree may not be balanced. In the worst case, the binary search tree can even be skewed, right? 就是说它就是朝一方这样子，就是朝一方这样长出来。In that case, like the search, the insert, the delete, I mean, suddenly becomes like very expensive, right? It could be like as worse as linear. So the idea of this what we call balanced binary balanced search tree is to come up with like strategy to make sure your search tree is balanced. OK？ 就这个所谓的 balanced search tree， 这些 balanced search tree， 他们就是想办法有一些办法去调整这个数，让这个数可以变成比较平衡。OK？ I mean, for example, for AVO tree, it guarantees like the left subtree, right subtree, the height difference is bounded by 1。就是 AVO 它的那个就是它保证它左指数跟右指数任何一个节点，左指数跟右指数的高度只差1。Okay, so that's like so how do they guarantee that? Basically, it's by certain type of like maintenance operation, okay, or what we usually call like rotations, okay, in the tree, okay, rotation. 就是你借由那个数的一些调整，可以把数的高度做一些修正。OK， 借由这些 OK through this maintenance OK operations, so the tree is balanced. OK, I'm not saying that it's completely balanced. I mean it satisfies certain property which is close to balance. For example, the AVO tree or like 2, 3, 3, 2, 3, 4 tree and B tree. Okay, so to be honest, I mean, I know we will not cover the other type of trees in today's lecture, but I highly recommend you to pick up the AVO tree and the B tree in your spare time. OK， 就是在你的，就是说有空的时间把 AVO tree 跟 B tree pick up 起来，因为 because these two search tree are very, very commonly used. Okay, so if you have taken data structure and algorithm, and then somebody asks you, oh, you do know AVL tree, you say, oh, I never learned that. You know, probably not a good idea. Okay, so at least you should pick up these two by yourself. AVL tree, B tree. Okay, and today we are going to focus on red-black tree. Okay, red-black tree is also a very interesting balanced search tree. Okay. Okay. Let me put it this way. Okay. It is relatively difficult to guarantee balance property. Okay. It's binary. The tree is binary. Okay. That is why you see the 2, 3 tree, 2, 3, 4 tree, the B tree, they are search tree, but they are not binary. They are not binary search tree. And the AVL tree is binary search tree, but it doesn't guarantee completely balanced. As I mentioned, like the height of the left subtree and right subtree difference is bounded by 1. That is AVL tree. Because like if you want a complete balance, it's difficult. Okay, for binary search tree. But red-black tree is binary search tree and it's balanced. Okay, well, solo, not complete balance, but at least it's very close to that. I will show that. So what is red-black tree? What is red-black tree? So red-black tree, this data structure, okay, requires actual 1 bit. We call it color, okay, in each node. Okay, in the tree node, we have 1 additional bit that represent color. Okay, and just by the name of this tree, okay, obviously we have 2 colors. 就是你就看这个树的名字 red-black tree， 我们就是2种颜色 ，black and red and black. Okay, so in the red-black tree, okay, there are 4 properties you have to maintain. Okay, in order to call a tree red-black tree. Okay, first, every node is either red or black. 每一个节点，要不然就是红的，要不然就是黑的。That's the first property. The second property, the root and the leaves are black. 就是树根跟树叶是黑的。And by the way, okay, we have a search tree. Okay, usually the purpose is to put some keys in there, right? So in the red-black tree, okay, the leaf nodes do not contain keys. Okay, 那个树叶节点它是黑的，没错，但是它不包含 key. Okay, and all the other nodes have keys, except the leaf node. Okay. Okay, the third property. If the node is red, its parent is black. Okay. So if this node is red, its parent must be black. Okay? The first three properties are relatively easy to understand. Okay? The fourth property is an interesting one. It's a little bit complicated. All simple paths from any node to its distant leaf, okay, have the same number of black nodes. 就是你从任何一个节点到它下面的树叶，任何的树叶，它的那个会经过的黑色节点的数目都是一样的。Okay, we call such a number as black height. So from any node, okay, because it from any node to its like distant leaf nodes, the number of black nodes that it traverses is the same. Okay, so we call that as black height. So here is the example of red black tree. Okay, so this is a tree of height 4, right? So you can see we have like a root, and we have some other nodes, and you can see that, okay, we have some leaf nodes, okay, but leaf nodes do not contain key, so we just write NIL for those leaf nodes. And first, every node is either red or black, okay, including the leaf node. Those NIL leaf nodes are black nodes, okay, we just didn't draw the node, we didn't draw the color, because those NIL leaf nodes do not contain keys, okay? So the first property is satisfied. Second, the root and the leaves, those NIL nodes, are black. Okay, the NIL nodes, I mean, even though we did not draw it, but they are black, by the way. And the third one, if a node is red, its parent must be black. If the node is red, its parent is black. So you can see every red node, its parent node is black, right? Okay, so this is like also, this property is also satisfied. The last one, the black height, okay? All simple paths from any node X to a distant leaf have the same number of black nodes. Okay, so for example, okay, from this node, okay, to its leaf node. Remember these two leaf nodes, they are black. So from this node to here, I mean, we have one black node. From this node to here, we have one black node. So the black height is 1. Okay, same thing, okay, from this node to any leaf node, okay, the black height is 1. Oh, by the way, we do not include this node itself. Okay, this node itself obviously is a black node too, but we do not count the node itself, okay, into the black height. Okay, and then, okay, this one, if you look at here, the black height is 2, because from here, for example, to here, we have 2 black nodes. This one. From this node to here, we have 2 black nodes. This one, this one. And from this node to here, we have like 1 black node, 1 black node. From this one to here, we have 1 black node, 1 black node. So the black height is 2. So the top one, black height is 2. The root node, the root, black height is 2 as well. Okay? So the property 4 is satisfied. Of course, this is just one example. Okay, I just want to show you. Okay, it is like relatively easy to construct to have such a red-black tree, and you might wonder, how come this is like, how come I call it balanced, right? It doesn't look like a balance, okay? Because left side, the left side of this tree is much shorter than the right side of the tree, right? The important thing is to look at those black notes. The black notes, no matter which path you take, you always have the same number of black notes, right? So if you only count black notes, in some sense, this tree is balanced, right? Okay, we will make use of this property to prove some stuff later on. Okay, I just want to point out, okay, this tree, even though it doesn't look like a balance, but it is like it has some balance property. Okay. So, since we want to claim this red-black tree is a balance, or the reason, I mean, why we want the, oh, by the way, I forgot to mention, this is search tree, right? Any questions that? A tree is a search tree if the in-order traversal result in sorted result in the sorted array, right? The sorted list of numbers. Okay? So I hope you still remember in order, what in order is. Okay? So in order, anybody can tell me what this one will give, this in order will give from this tree. 3, 7, 8, 10, 11, 18, 22, 26, right? Of course, I skip those NIL, because NIL does not contain keys. Okay, so that's the in-order traversal result, right? It's sorted. The numbers are sorted, right? So the reason why we want the tree to be balanced is because the height of the tree, okay, the height of the tree is bounded by log n. We want that to guarantee the operations, okay, the operation on the tree, such as search, such as insert, such as delete, take the log n amount of time, right? So that is like why we want to the tree to be balanced. So this tree, well, it's not exactly balanced, but at least we have this property, okay? A red-black tree with n keys has height, okay? This height must be smaller or equal to 2 times log n plus 1. So, how to prove this? Usually, when you want to prove some property of the tree, usually you use induction. And indeed, okay, if you are interested in reading the textbook at all, then you will see that the textbook used the induction to prove this theorem. Okay, but here, okay, we are trying a different approach. Okay, this approach is not. It's a little bit different, but what should I say? I would not say it's informal, but I would say it's very creative. Okay, remember what I told you earlier? Okay, if you consider only the black notes, the tree is balanced, right? Okay, if you only consider the black notes. So, yeah, the intuition is you can merge the red notes into their black parents. So how do we do that? Okay, we have a kind of like animation to show you how do we do the merge. Okay, so first, let me remind you, if a note is red, its parent must be black, right? So you must be able to merge the red note into the black note, right? And the second, okay, after the merge, it must be balanced, right? Because from any node, okay, from the root to any leaf node, okay, you have the same number of black nodes. You will traverse the same number of black nodes, right? That means the tree, after the merge, it must be balanced because we only have black nodes left, right? The third one, after the merge, how many branch do we have for one node? There are three situations. The first situation is this one. No red node gets merged here, right? So it remains to be two branches, right? Okay, this one remains to be two branches, okay, after the merge, right? So how about the other? If you have one node, one red node that merged, one red node child that merged to it, you have three branches. If you have two red node children that merge into you, okay, you have four branches, right? So number of branches will be 2, 3, and 4. Any question with that? That's it. There are only three cases. Okay? Because red-black tree initially is the binary tree, right? So the most number of red node that can merge into a black node is 2, right? So you at most you have 4 branches. Okay. So let's say after the merge, the height is h prime. Let's say the height is h prime. After the merge. The original tree, the height is h. After the merge, the height is h prime. Okay? So let me ask you this. What is the relationship between h and h prime? I mean like from root to any leaf node. At the most, you can only have half of the nodes that are red. Right? Because like, well, in the definition of the red tree, a red node must have a black parent. So in a path from the root to any leaf node, at the most you have only half red node, right? So in other words, this H prime, okay, is is greater than half of the H, right? Greater or equal to half of the H. Right? H prime is greater or equal to the half of the H. H prime is greater or equal to half of H. And how about number of leaf nodes? So we know like in a binary search tree, the number of leaf nodes is let's take a look at this one. The leaf nodes, they are leaf nodes, right? These are leaf nodes. And we know the leaf node is 1 plus the internal nodes, number of internal nodes, right? The leaf node is 1 plus the number of internal nodes, right? In any binary tree, right? And the internal nodes are the nodes that hold the keys, right? So if you have n keys, you have n internal nodes, right? So the leaf nodes is n plus 1, is that right? Is that right? So the leaf nodes, okay, after the merge, the leaf node stays the same, right? The leaf node stays the same. So the leaf node stays, this leaf node stays the same, right? So leaf nodes, okay, is n plus 1. Okay, this n plus 1 must be greater or equal to 2 to the power of h prime. Why? Why? Because, okay, for a binary tree, if a binary tree is of height h prime, let's forget about this. If I ask you, if you have a binary tree, if you have a balanced binary tree of height h prime, at the most, how many leaf nodes can you have? At most, how many leaf nodes can you have? It's 2 to the power of h prime, right? 对不对？就是如果说是那种 balanced and or complete balanced binary tree, the number with height h prime, the number of leaf node is 2 to the power of h prime. And we say like this n plus 1 is the number of leaf nodes here, right? I would say this n plus 1 must be greater or equal to this one. Why? Because we are not talking about binary tree here, right? Here, like the nodes could have like more than 2 branches, right? So number of leaf nodes is at least 2 branches, right? The branch is for each node here, the branch is at least 2. It could be 3, it could be 4, right? So the leaf nodes must be at least or greater or equal to 2 to the power of h prime. Okay? Right? And then if you have that, you apply log on both sides. It's going to be log n plus 1 greater or equal to h prime. And we know h prime, as we discussed earlier, h prime is greater or equal to half of h. So that's why we have this. Right? Any question here? So, for a red-black tree of n keys, for red-black trees of n key, we know the height is bounded by roughly twice of log n, right? Twice of log n. So it's it's not log n, but it's bounded by twice of log n. So it's still good enough. Okay, it's still good enough. So the search min max successor predecessor all runs in big O log n time on red-black tree with n nodes. Why? Because all these operations, okay, the worst case is from root to one of its leaf nodes, right? And because the height is bounded by 2 times log, well, n plus 1, okay? So it is all this operation will run in big O log n, okay? How about insert and delete? Okay. Because these operations, the search, min, max, successor, predecessors, all these operations do not involve in modifying the tree structure. Okay, so it is relatively easy to talk about their complexity. But insert and delete will modify the tree property. So yes, I mean we need to discuss that. Okay, insert and delete. So in the end, you will see that the insert and delete also takes like log n amount of time. Okay, but how to do that? We will only show insert. Okay, delete. I mean, I'll leave that one for you guys. Okay, to study by yourself. Okay, but remember, I mentioned earlier. Okay, the balanced tree. Well, even though this red-black tree doesn't look like a balanced initially, but yeah, remember what I told you. If you only consider like a black node, it is balanced. Okay, it is balanced. So yeah, I mean any balanced tree. Okay, if you want to maintain the balanced property, it must involve certain rotation, okay, operations. So yeah, that is what we are going to talk about. The modifying operations include insert and delete. It's going to cause modifications of the red-black tree. Okay, so the operation, okay, this operation include the operation itself, and the color changes, and also restructuring. Okay, the restructuring is what we call rotation. Okay. So how do we do it? First, let's talk about the rotation. Okay. We have two different rotations. One is right rotation, one is left rotation. Okay. From left side to right side, we call this is a right rotation. From right side to left side, we call it left rotation. Of course, it's with respect to a node. Okay, right rotation, we move B to right, so we let B to go down. And the left rotation, okay, we let A to go down. Okay, to become this. Okay, so here, okay, keep in mind that after all, we are dealing with like search tree, right? We are dealing with binary search tree. So this rotation must guarantee the binary search tree property. Okay, so you can see that, okay, from left to right or from right to left, okay, regardless what the direction, okay, the in-order traversal always is always maintained. Okay, for example, in order you are going to deal with alpha, this subtree, and then capital A, and then beta, and then capital B, and then gamma. Okay, and here, okay, you look at here, the in-order traversal, you are going to deal with alpha subtree, and then capital A, and then beta subtree, capital B, and the gamma subtree. That will be exactly the same, right? So this rotation does not change the balance. Does not change the binary search tree property. Okay, we need to guarantee that. Otherwise, if it breaks the binary search tree property, then we lost like the purpose. Okay, we lost the purpose. And we can see that this rotation, no matter we are doing the right rotation or left rotation, this rotation, it takes only constant time, okay, to be complete. Right? Because you need to, from left to right, okay, you need to promote node A, okay, and so you basically, assign the parent of B to node A, and then assign the parent, change the parent of B to point to node A, okay, and then change the left child of node B to the right child of node A to here. Okay, and the vice versa. Okay, you can see that. The rotation, no matter it's left rotate or right rotate, it takes a constant number of operations. So that's why we say this rotation, no matter which one, it can be performed in big O1 amount of time. To be exact, it involves the change of 3 pointers. The change of 3 pointers. Okay? So then, let's consider inserting a node, a key, to a red tree. Okay. Well, let's take 10 minutes break first, because like this one, I mean, I think like we won't be able to finish like this one in 2 minutes, which will be the remaining time, I mean, before the break. So let's take break first, and then when we come back, we are going to finish this part, and that will be the end of this lecture. Okay, so we probably will be done a little bit earlier. Okay, but you know, I have to pick you know, I have to pick a lecture that I can guarantee to finish before the time runs out. Right? Because like obviously like this today is the last day, last lecture before the midterm. Okay, so I picked this lecture to make sure I can finish in time, on time. But yeah, obviously like my estimation is a little bit off. Okay， 就是我必须要选择一个 lecture， 是我足够有时间可以把整个解释完的。但是这个时间有点那个比我想象中的快一些啊。哦，顺便有一件事情 ，another thing to mention. Okay, so next week is the midterm, right? Okay, you guys all know about that. And the week after next, okay, we have like a regular class, but because that day is the department is going to be reviewed. Okay, 我们系要被那个，就是刚好是那个礼拜三，就是下礼拜三，我们系要被这个评鉴。Okay, so because I'm a department chair, so I have to be there to present like the department's like status and all the stuff to be with those like the visitors， 就那些评鉴委员，我必须要跟他们在一起。就是下礼拜三的早上。So in other words, the week after next, the lecture will be conducted by my PhD student. Okay, so he will cover amortized analysis. Okay, so yeah, I apologize that I cannot be here the week after next because of the department matter, okay, department issue. But that class will not be canceled. My student will cover that. Okay. Just want you guys to be aware of that. Okay. So let's take 10 minutes break. When we come back, we'll discuss this.